Our second speaker this morning is Garrett King. He works in theoretical nuclear physics at Washington University in St. Louis. He also did a practicum at Los Alamos in 2022. Garrett, please take it away.
So, thank you for the introduction. I'm going to be talking about the thesis work that I carried out at Washington University in St. Louis before going on to my postdoc at Los Alamos, which is focused on lepton-nucleus interactions, and particularly the nuclear structure aspects of those and how those can contribute to ongoing searches, trying to probe the fundamental symmetries of the universe and look for new physics. But before we get into fundamental symmetries and what new physics searches are going on, it's a good idea to cover the fundamental physics that we already know about, and to kind of give you a sense of what those symmetries are. And so here I'm showing just the standard model of particle physics, which has breaks up the universe into different fields that transform with certain symmetries in space and time. And so we group the different generations of matter, of which there are three, into two different types, quarks and leptons, that are differentiated by how they couple to the force-carrying gauge bosons, which are responsible for mediating 3 out of the 4 fundamental forces that we know about in nature, as well as the famous Higgs boson. And so to connect this with what we understand, I'll just go through it really fast. So the up and down quarks combine with the gluons that mediate the strong interaction to give rise to the protons and neutrons inside the nucleus that we're all familiar with, and gives rise to the rich variety of nuclear structure phenomenon that we observe. But in addition to the atomic nucleus, we also have the electrons and the electromagnetic interaction that's mediated by the photon that couple together to give us the chemical elements and the vast array of materials that we observe and interact with day to day. And finally, we have a bridge between the quark and lepton sectors in the standard model that's mediated by the W and Z bosons, which are responsible for the weak interaction, where we have particles like quarks being coupled to leptons. And that's what I'm going to focus on today, talking particularly about nuclear beta decays. And of course, we have the Higgs mechanism that's responsible for generating most of the mass within the standard model. But while this is a very successful theory and capable of making extremely accurate predictions, it's starting to show some cracks. And in particular, I drew those on the neutrino section, the cracks that we're starting to see. The reason being that the first evidence that we had that there's some physics that's not accounted for within the standard model was the observation of neutrino oscillations. And so I had mentioned before that the Higgs mechanism is responsible for generating most of the mass within the standard model, but there's no way through the Higgs mechanism for neutrinos to have a mass. So they're predicted to be zero mass objects within the standard model. However, this observation of neutrino oscillations was an indicator that neutrinos have to have at least 2 non-zero mass states out of the 3 available. And so we already know that neutrinos have mass, so there's something that we're not accounting for. Additionally, we can look at the energy distribution of the universe and see that the normal matter that I was just telling you about, composing the standard model, makes up only about 1/6 of all the matter that we see out there, with the remaining 5/6 of it being composed of dark matter. In addition, when we look at the energy distribution, we see that 70% of that isn't even matter, but dark energy. And both dark energy and dark matter are lacking an adequate description within the standard model. And so a fundamental theory of the universe is going to have to account for those as well. And finally, when we look out at the universe, we see there's an observed asymmetry between matter and antimatter. And so any fundamental theory of the universe will also need to account for this asymmetry. So we know that there's signatures of new physics, but the question then becomes, where can we start to look for that? And so one place where we can look is at standard model processes that are allowed, like nuclear beta decays, and look for deviations between what we expect and what is observed experimentally to try to find some anomalies. We can also search for processes that are rare and not permitted in the standard model. One of those is an area known as neutrinoless double beta decay, where they look for a process that would be a smoking gun signature of new physics, because we know that it couldn't occur with the physics that we know of so far. And finally, we can look at the beyond standard model physics that we know of, like neutrino oscillations, to better probe parameters associated with that to try to put constraints on potential models for new physics. And so as I mentioned, I'm only going to focus on one lane here in these searches of the precision frontier. However, the many-body methods that I'm going to talk about have the potential to contribute to all three of these directions. And so why are nuclear beta decays in particular something that is interesting to look for new physics, at least according to me? And I think it's because you have this bridge between the weak sector where you start with something that's just an atomic nucleus, and then we have a neutron being converted into a proton, but then also two leptons, so an electron and an electron antineutrino. And we know that the neutrino sector is where we're starting to see signatures of new physics from neutrino oscillations. So we get a direct connection to the area where we know there's new physics, but we can use atomic nuclei to probe that. And so in these experiments, we have access to not only the energy of the recoiling nucleus, but also the energy of the electron that gets emitted, as well as the angular correlation between the electron and the neutrino. And so if we have a precise prediction for what those kinematic variables should look like, then we can look for deviations from that and distortions of those variables to see whether or not there's some signature of new physics and to put constraints on what symmetry it might have. And so in order to get to that level of having a very precise prediction, we need to turn to solving the quantum many-body problem. And so the general idea here is that we have the atomic nucleus that's involved in the decay process, which is composed of protons and neutrons, which I'll collectively refer to throughout the talk as nucleon degrees of freedom, that are moving around inside the system and interacting with one another, and also exerting statistical effects on one another because they're fermions. And so those interactions and statistical effects generate entanglement in solutions of the Schrodinger equation that have to be accounted for in your many-body method. And so we're just solving this equation, h psi equals e psi, to try to get the wave functions that we're going to need to go into predictions of observable quantities. Whoops. And so the approach that I use is quantum Monte Carlo, where we retain the full complexity of the many-body wave function for A nucleons, containing information about the 3A coordinates in space, as well as the spin of the nucleons. So these are spin 1/2 fermions that can take on two different states, up or down, which gives you 2A possible different spin states. And then isospin, where you can look at the proton and neutron like being two different spin states, which gives you a combinatoric factor that's restricted just from the fact that charge is conserved inside the nucleus. But when you look at the size of this wave function, which grows exponentially with the number of particles, you see that already going from a system with 4 particles like helium-4 up to something like carbon-12, where now we've put in 8 more particles, we've generated a dimension for our wave function that increases by about 5 orders of magnitude. And so this is a problem that even for light nuclei requires us to use supercomputing resources in order to perform our many-body simulations and to try to obtain our wave functions and then make predictions of observables. And so, as I mentioned, the methods that I use fall under the suite of quantum Monte Carlo methods, of which I'll discuss 2 today in this talk. And the way that I work on the problem is a 2-step approach, which begins with variational Monte Carlo. So we're trying to solve the Schrodinger equation h psi equals e psi. And the way that we do that is by leveraging the variational principle, which says that we can start with some trial ansatz for our wave function, and we know that the energy that we generate when solving the Schrodinger equation with that ansatz is going to give us an upper bound to the true ground state energy of our system. So we can construct an ansatz that's factorized into 2 different parts, a mean field description of the nucleus here represented in blue, where we put protons and neutrons into different, in this basically extreme shell model picture where we put protons and neutrons into the S and P shell. And then that encodes the long-range structure of our system and also gives us the right quantum numbers for the system that we're looking at. But then on top of that mean field picture, we have to account for the interactions between the particles in the system. So we have this correlation operator here in pink that depends on the coordinates, spins, and isospins of the particles in the system. And embedded in that correlation operator are variational parameters. And so when we solve for the energy expectation value, which just requires evaluating Monte Carlo integrals, we're then able to minimize the energy expectation value by optimizing the variational parameters in our wave function in order to get an upper bound to the ground state energy of the system. However, this is only an upper bound, and we can always do a little bit better than that, or in fact try to get as exact as possible. And that's where Green's function or diffusion Monte Carlo comes in. So this leverages the fact that we can recast the Schrodinger equation in real time as a diffusion equation in imaginary time by making a change of variables from it to this variable tau. That then, when we perform the sampling of the resultant path integral in imaginary time with Monte Carlo, as we take it to time going to infinity, we'll project out something that's proportional to the true ground state of our system. So here I've shown a schematic where we start with some walkers and just a 1D instead of a high dimensional configuration space that we allow to evolve in imaginary time, where the random steps are sampled according to this path integral approach, and it gives us an exact solution to the Schrodinger equation. Finally, we want to compute nuclear matrix elements with this procedure, where we have some initial wave function psi alpha acted on by an operator O, that we then look for how similar the resultant wave function after that action is to some final state wave function psi beta, which can be related to physical quantities of interest like decay rates, half-lives, cross-sections, and whatever you might be interested in computing. And so the operators that I work with are electromagnetic and weak charge operators that can schematically be broken down into single nucleon terms where one nucleon inside the nucleus interacts with an external field, and then these correlation terms where pairs of nucleons are interacting with the external field simultaneously. And these two-body effects can actually have important impacts on observable quantities. So here I show an early work that I performed in my thesis studying beta decay rates with two different models used to fit the nuclear interaction, which changes one specific term in the two-body currents. And you see that when you look at the pink model versus the blue model, with just the one-body current operators versus these two-body currents containing those correlated pairs, you see that you get a difference in the overall size of the two-body effects coming from one model to the other, which naively one wouldn't expect. And so it indicated that there's this bias from the fitting procedures on this percent level effect. Except for in the case of A equals 8, where it's more like 20 to 30%, but I can maybe field some questions on why these decays are more complicated later. But the idea then with these different models that we validated against experimental data and looked at the effect of two-body currents and how they're fit was to try to make connection with this differential decay rate for the helium-6 beta decay spectrum that's proportional to the square of a nuclear matrix element times a kinematic factor. However, new physics effects can distort that kinematic factor with this characteristic electron mass over electron energy dependence. But this is all done in an approximation of no recoil to the nucleus. And so if you account for both two-body effects and recoil corrections, you should be generating corrections that are on the size of the distortions that experiments are currently trying to probe. And so that was the main goal of the next step of this work, was to compute the 4 nuclear matrix elements that go into this beta decay spectrum. Oops, sorry. This beta decay spectrum as a function of the momentum that's transferred to the nucleus, and then to make predictions of how the spectrum gets distorted. So here I'm showing the distortion of the spectrum as a function of the energy fraction carried out by the electron. And you see that when you account for those two-body current effects and recoil, you can generate distortions of about 1% on the overall spectrum. But when you look at the integrated rate, you find pretty good agreement with the experimental data. And what this allowed us to do when accounting for the uncertainty from the different approaches to fit the nuclear model was to look at how new physics scenarios would be impacted for this ongoing experimental effort that's being made to measure the helium-6 beta decay spectrum with per-meal precision. And so on top of the standard model prediction that I just showed, we could include new physics scenarios with a field that transforms like a pseudoscalar or a tensor. And we see that ongoing analyses would have sensitivity to tensor and pseudoscalar contributions at the level currently allowed by collider analyses for the tensor, maybe not so much for the pseudoscalar. But if these per-meal precision experiments are able to get the precision they're aiming for, then we would be able to probe physics at the 1 to 10 TeV scale, which is comparable with the physics searches that go on with these large collider experiments like the Large Hadron Collider at CERN. And so just to conclude, so many-body calculations with modern nuclear interactions are important for helping us to understand the impact of nuclear dynamics, like two-body currents, on electroweak structure. And we can understand the role of nuclear structure and two-body effects on different observables like beta decay rates and spectra, and then we can use our models to make connections with analyses of beyond standard model physics. And before I wrap up, I just want to acknowledge all of my collaborators who made this work possible, and in particular my advisors, Sari Pastore and Maria Pio-Rulli at Washington University in St. Louis. And of course, thank you to the SSGF for the financial support that made this work possible. So thank you.